Beneath our feet, a silent drama unfolds as tectonic plates collide in a geological dance that occasionally unleashes devastating earthquakes. For centuries, predicting these catastrophic events has eluded scientists, until now. Join us as we explore how cosmic muons, subatomic particles raining down from space, are revolutionizing earthquake forecasting and potentially saving countless lives. This remarkable convergence of particle physics and geology may finally give humanity the early warning system we've sought for generations. Cosmic muons are subatomic particles produced when cosmic rays from deep space collide with Earth's atmosphere. These elementary particles continuously bombard our planet at nearly the speed of light, penetrating hundreds of meters into solid rock. Unlike conventional imaging technologies that struggle to see through the Earth's crust, muons interact differently with matter depending on its density, effectively creating a natural scanning mechanism that scientists have learned to harness. These invisible particles pass through us by the thousands every minute, carrying valuable information about what lies beneath the surface. The emerging field of muon tomography captures variations in muon penetration to develop three-dimensional density maps of subsurface structures with unprecedented precision. This technology represents a paradigm shift in how we monitor the hidden processes along fault lines. While muon tomography first gained recognition for volcano monitoring in the early 2000s, its application has recently expanded to earthquake prediction. The breakthrough came from Dr. Hiroyuki Tanaka, who first demonstrated muon radiography's potential by imaging the interior of Mount Asama volcano in 2007. His team's innovations in detector design reduced background noise and increased sensitivity, making the technique viable for detecting the subtle density changes associated with pre-earthquake conditions. In March 2023, researchers at the Tokyo University of Science made a critical advancement by deploying a network of muon detectors along Japan's Nankai Trough, a major subduction zone responsible for magnitude 8+ earthquakes. Their preliminary findings, published in Nature Geoscience, revealed previously undetected density anomalies that preceded minor tremors by 3 to 5 days. The detection system measures muon flux, the rate at which these particles pass through Earth's crust. Subtle changes in this flux can indicate stress accumulation or fluid migration within fault zones before conventional seismographs detect any activity. Unlike traditional methods that rely on surface measurements, muon tomography provides a direct window into the processes occurring at the exact depths where earthquakes originate. The technology behind muon detection has evolved dramatically in recent years. What began as bulky, expensive laboratory equipment has transformed into more compact, field-deployable units capable of operating autonomously in remote locations. Each modern detector consists of specialized scintillation plates that flash when muons strike, with the patterns captured by highly sensitive photomultiplier tubes. This approach's ability to monitor changes over time makes it particularly valuable. Static images of subsurface structures provide useful information, but the real predictive power comes from tracking gradual shifts in density patterns that might indicate increasing stress or the movement of groundwater into newly formed microfractures, often precursors to larger seismic events. Following Japan's promising results, the International Muon Seismic Alert Network, or IMSAN, was established in September 2023. This collaborative effort has installed 47 detector arrays across 5 continents, focusing on high-risk seismic zones. The network's most significant achievement came in January 2024, when detectors in Chile registered anomalous muon patterns 72 hours before a magnitude 6.2 earthquake near Valparaiso. While not a definitive prediction, this provided enough warning for authorities to implement precautionary measures, potentially saving lives and demonstrating the technology's practical value. Dr. Elena Vazquez, IMSAN's coordinator, emphasizes the importance of this distributed approach. Earthquakes don't respect national boundaries, and neither should our monitoring systems. We're creating the first truly global seismic early warning infrastructure by standardizing detection protocols and freely sharing data across borders. This international cooperation represents a marked departure from previous earthquake research, which often remained siloed within national geological surveys. The detector placement strategy follows a carefully optimized model developed by seismologists and particle physicists. Priority locations include obvious fault lines and areas where tectonic plates interact more complexly. The San Andreas Fault in California now hosts 9 detector arrays, while the lesser-known but potentially catastrophic Cascadia subduction zone features 7 installations, stretching from Northern California to British Columbia. This strategic placement ensures comprehensive coverage of the most dangerous seismic zones, creating a network that can detect subtle changes across vast geological formations. The vast amounts of data generated by Muon detectors present formidable computational challenges. A single detector array produces approximately 2.7 terabytes of data daily, requiring sophisticated analysis methods to extract meaningful patterns. This is where artificial intelligence has become indispensable. Researchers at Stanford University recently developed MuonNet, a specialized deep learning algorithm that identifies subtle correlations between moon flux variations and subsequent seismic activity. The system continuously improves through a feedback loop, comparing predictions against actual earthquake occurrences. After analyzing historical data from 2018 to 2023, MuonNet achieved a 63% success rate in predicting earthquakes above magnitude 5.0 within a 3-day window, a significant improvement over the previous 30% baseline using conventional methods. Dr. Wei Zhang, lead developer of MuonNet, explains, "We're not just looking for simple threshold crossings in Muon counts. The AI identifies complex spatio-temporal patterns across multiple detectors, correlating them with historical seismic events while filtering out environmental noise." Perhaps most remarkably, MuonNet has begun identifying what researchers call seismic fingerprints, unique patterns of density changes that characterize specific fault systems. An earthquake preparing to occur along California's Hayward Fault produces muon flux patterns different from those developing in Japan's Nankai Trough. The AI has become increasingly adept at recognizing these distinctions, creating a catalog of fault-specific signatures that improves prediction accuracy. The algorithm also incorporates traditional seismic data, meteorological conditions, and even subtle gravitational variations measured by satellite systems to improve its forecasts, creating a multidimensional approach to earthquake prediction. Despite promising advances, Muon-based earthquake prediction faces substantial challenges. The technology requires dense detector networks for accurate mapping, with each unit costing approximately $180,000. Additionally, factors unrelated to seismic activity, such as atmospheric conditions and solar activity, can affect muon flux, necessitating complex filtering algorithms to separate signal from noise. Perhaps most importantly, the field must navigate the fraught history of earthquake prediction, where premature claims have led to public panic or complacency. Scientists emphasize that muon tomography offers probabilistic forecasts rather than precise predictions, similar to modern weather forecasting. This nuanced approach requires careful communication with the public and policymakers to ensure appropriate responses to warnings. The January 2024 Valparaiso earthquake in Chile provided the first real-world test of the muon detection network. When detectors registered anomalous patterns 72 hours before the magnitude 6.2 event, authorities implemented their emergency protocols. Schools conducted earthquake drills, hospitals reviewed disaster plans, and utility companies prepared emergency response teams. While the earthquake still caused damage, the preparation time allowed by the muon detection system significantly reduced casualties and enabled faster recovery. This case study demonstrated that even with the technology's current limitations, the additional warning time provides tangible benefits to communities in seismic zones. As detector technology becomes more affordable and machine learning models more sophisticated, muon tomography represents our most promising avenue yet for transforming earthquake prediction from science fiction into reality. The IMSAN consortium plans to expand to 200 detector sites by 2026, potentially creating the first global early warning system capable of providing hours or even days of advance notice before major seismic events. The implications extend beyond public safety. Insurance companies have begun funding research, recognizing the economic value of more accurate risk assessment. Urban planners are incorporating muon-based hazard maps into long-term development strategies. Engineers are designing structures that can be rapidly secured when warnings are issued, potentially preserving critical infrastructure during major events. Perhaps most profoundly, this technology represents a unique synthesis of fundamental particle physics and practical geoscience, a reminder that solutions to earthly problems sometimes come from understanding the cosmos itself. The muons that enable this revolutionary approach to earthquake prediction originate from distant cosmic events, traveling light years before reaching our atmosphere and cascading down to provide insights into our planet's interior processes. This connection between the infinitely large and the microscopic, between theoretical physics and practical disaster prevention, highlights the unexpected ways scientific disciplines can converge to address humanity's most pressing challenges. The story of cosmic muons and earthquake prediction represents one of the most promising intersections of fundamental science and practical application in recent decades. By harnessing particles born in the distant cosmos, scientists have developed a window into the Earth's most destructive geological processes. While challenges remain in detector cost, data processing, and prediction accuracy, the rapid advancement of this technology offers hope that we may soon enter an era where earthquakes, while still inevitable, no longer strike without warning. The International Muon Seismic Alert. Network's expansion to 200 sites by 2026 could fundamentally change how communities in seismic zones prepare for and respond to these events. As this technology matures, it stands as a powerful reminder that scientific progress often comes from unexpected connections between seemingly unrelated fields, in this case, between particles from space and the ground beneath our feet. The Muon revolution in seismic forecasting demonstrates that even as we continue to explore the universe, some of our most important discoveries may help us better understand and protect our home planet. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.